Hello and welcome to today's webinar about the multidisciplinary optimization of a subsea construction vessel. This webinar is brought to you jointly by Kongsberg Maritime and Friendship Systems and will cover material that was produced within the R&D project Holiship that I will introduce briefly a bit later. So, my name is Matthias Brenner and I will be your host and moderator today. I'm currently responsible for sales at Friendship Systems, and I have worked several years in the pre-sales and engineering departments here. Before that, I've been with Friendship Systems for about 13 years now, and I'm a naval architect originally. On Kongsberg's side, we have Paulo Macedo with us today. He is a design and simulation specialist at Kongsberg Maritime. He used to be a colleague. He wrote his master thesis at Friendship Systems, which was also part of the Holiship project about a swath vessel. And he has been with Kongsberg Maritime since 2018, and he's also a naval architect. And finally, I'm also joined by my colleague Heinrich from Friendship Systems. He's a support engineer here. He also wrote his master's thesis at Friendship Systems, and he has been with us for almost 4 years now. He's not a naval architect, but he's an engineering science master. So before we actually get started, I have just a few brief housekeeping issues to mention. Today's webinar will be recorded, so it will be available for replay later on. You will get an automated email with a link, and later on it will also be available on our website or YouTube if you want to share with some colleagues or the likes. At the end of the webinar, with the time we have left, we want to make a short Q&A session. So if you have any questions that come to your mind while listening to this webinar, you can submit them directly in the interface of the GoToWebinar, and we will try to address all of them or as much as possible at the end of the webinar. So let's get started. I have just a very brief introduction about Friendship Systems. I think many of you attendees are familiar with us, but some of you aren't. So who are we? We are a company located in Potsdam, Germany, and we specialize on solving problems in the simulation-driven design process. And we have more than 15 years of experience in the fields of geometry parametrization on the one side and optimization of these geometries in connection with different simulation tools or other calculation tools. We started in the maritime industry, but now we are active in also several other industries where shape optimization issues are of importance. And our business is mainly connected to our software product, which is the CAE platform CAESES. This is a brief overview of what CAESES does. You see we have basically 3 components. The first one is a specialized CAD system that is focused on geometry variation, especially of complex, most of the times freeform geometries, and is able to parametrize these kind of geometries in an efficient way so that they can be used in the optimization process and that they can produce in a robust way clean geometries that can then be fed into the next component of the system, which is what is called automation here, which is basically the interfacing of CAESES to external computation simulation tools that take these geometry variants that we generate with the CAD component and analyze them in some ways and feed us back some results or some measures of merit that can then be used in an optimization process, which is the third component of CAESES, the optimization environment, which provides all the necessary algorithms to run an optimization or systematic parameter study but also post-processing tools to analyze the results, data management to manage all the geometry and simulation data that is being created, and finally gives the user all the necessary tools that he needs to make a design decision based on what has happened. And finally, here is just a quick view of the user interface of CAESES. We'll see more of this than in Heinrich's part of the presentation. I mentioned that the work that is being presented in this webinar today was part of the so-called holiship project, and I want to briefly introduce that so that you understand the context. Holiship stands for Holistic Optimization of Ship Design and Operation for Life Cycle. It was a large European publicly funded R&D projects that included 40 partners from industry and academia, and it was funded within the European Union's Horizon 2020 Transport Research Program with the aim to develop the next generation ship design system for the European maritime industry. Quickly about the motivation of this R&D project. I think most of you are familiar with this typical design spiral of ship design. You are aware we have many requirements to the design of a specific vessel that need to be taken into account in the design process. They go from hydrostatics, hydrodynamics, structural requirements, powering, stability, things like that. And according to this model of the design spiral, typically these requirements are taken into account one after the other and incorporated into the design. And then the whole process is repeated in several iterations until all the requirements are fulfilled and we have converged into a design that is suitable for the task that it was designed for. And the idea here is to basically, rather than go through these different disciplines step by step and repeat them iteratively, is to synthesize everything together and take it into account in one go, define all the requirements, build them into the model, and then evaluate all of them together during the optimization process. For the project setup, the holiship project was divided into a few different clusters. We have cluster 1, which you can see here in red, which basically comprised the development of individual tools that are used in the design process. So all the project partners that were in charge of these packages here worked on different tools and develop them or further develop them if they were already existing. Cluster 2 is the integration of these different tools. So basically the creation of different platforms that are able to connect these tools together and integrate them into one design process. And this is where we at Friendship Systems were mainly working. We were the project leader of work package 7, as you can see highlighted here. And finally, the third cluster refers to the application cases, so different design cases that were carried out using the tools developed within this project. And the application case that we will see today is part of this cluster 3. And now I will give over to my colleague Paolo from Kongsberg, who will introduce this application case and talk about that some more.
Hello, everyone. Thanks, Mattia, for the introduction. Thank you for introducing myself and your company and holiship. I'm going to talk about the work package 9, where we holistic design an offshore support vessel. Firstly, Kongsberg Maritime, as many of you know, it's a rather very large enterprise. We offer from integrated solution from design until the final integrated support on site, propulsion and engines, sensor robotics, deck machinery, motion control systems, and 24/7 global customer support. Any other question you have, just visit our website to get in contact with our people. Holistic design of our offshore support vessel. It's specific for subsea operations. It's fitted with an offshore fiber rope crane that can lift up to 250 tons, or a steel wire crane that can lift 400 tons, including the steel wire weight. It was divided in 3 main phases, where we start with hull and propulsion dimensioning, concept design phase used by mostly with CAESES and all the calculation tools. These designs are down selected and sent to the next phase, which is power system and design optimization, developed partially by Kongsberg, Cosmos, from DNVGL, Sirena, and Bureau Veritas doing RAM analysis. And then in phase 3, we had a power system verification of the design system in phase 2 at real-time simulator in Ålesund, Kongsberg simulator. Phase 1, it is that design spiral. Now it's not a spiral anymore, but all the tools are connected at the same time from the hull until the fuel consumption calculation. Here you can see from 1 to 8 the phases, what goes inside and what comes outside, and I'll go through it in more detail now. Starting with hull design, we had a vessel UT 7623 from 2018. Now, as a baseline, we made some main dimensions, design, and bulbous bow adjustments. We parameterized these transformations, and we always, in order to create these designs, and we can always follow the hydrostatics of it as we go. I would like to invite now Heinrich to do a live demonstration of these transformations on a hull vessel.
Thanks a lot, Paolo, for letting me interrupt and take over this presentation for maybe the next 15 minutes. This is a very complicated application case that we're looking at here, and it comes with a rather sophisticated setup, I would say. For us at Friendship Systems, it's always nice to see that there's customers and power users of CAESES that they use our tool to such an extent. But for this presentation, I would like to sort of zoom out a little bit and take a closer look at one of the fundamental building blocks that is, that is needed for such a process. In one of our recent webinars with Allomatic, which was also part of holiship, we have talked a little bit about fully parametric modeling within CAESES, which is why this time I would like to focus on partial parametric modeling techniques in particular. What we're looking at here is an imported geometry that was given to me by Paolo prior to this webinar. And I would like to showcase to you a little bit how such a hull model can be modified step by step through the use of partial parametric modeling techniques that we offer in CAESES. So what I did is I started by changing the bulbous bow of this vessel, put some section visualizations here so that we can see better what's going on. And I've set up this deformation box here. And what I can do there is I can set a number of layers inside of this box and thereby generate a number of control points, which I can modify individually. And I can address those points through a design variable, which I've done here. So for example, if I change this design variable called thickness, you can see those points moving out, moving left and right, if you will. And you can already see in the background there that the hull shape follows along. So if I hide this model, the deformation box, and maybe turn on the mirroring here, you can see very clearly how I can change the thickness of the bulbous bow through the use of this deformation box. So that's a very easy way of modifying an existing geometry. And by making sure that we don't move any points that are too close to the boundary between the B-spline volume and the existing hull, I can make sure that we maintain continuity towards the remainder of the hull. What I also did here is I allowed those points to move up and down, and thereby I can shift volume inside of the bulbous bow up and down, as you can see here, if I change this design variable from a high to a low value and vice versa. Next, I decided I would like to change the length of the bulbous bow. Could have done this just as well in the freeform deformation by just pulling the points fore and aft. But for demonstration purposes, I've chosen to use a delta shift in this case. So I've set myself up this function down here, which is controlled basically by a point at the very tip, which in turn is controlled through this design variable. So if I increase the value, the point moves up, and you can immediately see that the bulbous bow is elongated. And the other way around, I can also decrease this value, and I get a shorter bulbous bow, as opposed to, for comparison here, the initial length of the shape. What happens here is that this function is basically looked at, and at every longitudinal position, we would extract the vertical component here and use this number as a horizontal shift of any geometry right above the function. That also means that, as you can see here, the upper portion of the hull follows along, so I'm not just changing geometry down here. If I would want to limit my deformation to this lower area, I would have to set up another delta shift and combine those two in a delta product, which is exactly what I've done here in the next case when I change the height. So for this folder, I've again set up a delta shift, works just the way as the one that I've shown to you earlier. So again, if I move this point up, the bulbous bow would follow along and move up. But this time, if you look closely up here, the tip of the vessel doesn't move up and down, so it doesn't follow. And the reason it stays fixed in space here is that I've set up this second delta shift function. If I look right from the tip, you can see here, this function is constantly 1, which means 100% below the waterline, and then it smoothly fades out towards the tip so that we apply 0 transformation up here, and then more and more when we go down this way. And this is how you can limit the effect of a delta shift to a certain range. The next bigger thing, so to say, after delta shifts would be surface delta shifts. They work very similar, except that they allow you to use an entire surface as an input. So I've created this planar surface, I've parameterized it, so there's a couple of points I can move around through the use of this design variable here. And as you can see, I've put some isolines so that you can see that this would generate a slight little hump in the middle of the surface. I can move this left and right just as well. And what happens is that we can set a projection direction, so to say, and project this deformation to the geometry right behind it. So if we look at the forward shoulder of the vessel here, we can see that there is volume removed right now, and I can add volume by increasing this design variable and make the hull a lot fuller in this region. And these two parametrics, they usually work together very well. So changing the bulbous bow, making it longer, wider, shifting volume up and down, and at the same time changing the forward shoulder of the hull, because those two, they both have an impact on the wave field that develops. They both have an impact on how waves would interfere with each other. So if I change one, I need to change the other in order to counterbalance, so to say. And if I have both modifications in my model, I will potentially get good improvements in wave resistance, if that's what I'm after. I've added 2 more delta shifts to this model, which allow me to change the midframe They are both, again, delta products. And what they do is one allows me to add dead rise. That means I can bring up the flat of bottom here from a horizontal flat of bottom to a certain angle without lifting the deck. And the other one is flare, which allows me to angle the side of the vessel here, as you can see, at the same time, again, without shifting any geometry across the symmetry plane. So I've used a delta product again here to fade out this transformation. So that is so far 1, 2, 3, 4, 5, 6 deformations used in total, and they all are applied one after the other. So I started from an imported BREP. I create a new one, which receives the freeform deformation, create a new one, which receives the first delta shift, and so on and so on. Once I've done this and set up everything, I can just as well create one BREP that starts from the initially imported BREP and receives one final delta sum. And this delta sum would then contain all of the deformations. And the reason I'm doing this is because that improves performance again quite significantly. So we can see if I change one of the, so to say, very early design variables, like the height of the center of buoyancy of the bulbous bow, that triggers a full model refresh here. Everything needs to update, and it does so within, that's probably less than 2 seconds here. So it's very nice to work with this model because it's very responsive. I would now like to continue with some deformations that would have not been possible in our earlier versions of CAESES 4 because they use what we call Birthmorph. That's a partial parametric modeling techniques that is completely new, introduced in CAESES 5, and allows us to move geometry. In most cases, there would be BREPs, and match certain source and target geometries. That means we can set source and target points or curves or surfaces and tell the BREP that we want it to change in shape so that it would deflect and change from one shape to the other. That becomes a bit more clear if I explain my first transformation here. I've set up this curve, which is basically an intersection of a plane with my initial shape. And I've set up another curve in space. I can freely control the shape of this curve by moving around these control points. Maybe I want to move this aft point here a little further out. That's totally up to me where to put that curve. And then, as you can see, as soon as I apply the morphing, my geometry changes and switches from the old shape to completely match the newly given curve. And the beauty here is I can also match anything in between. So I don't have to apply 100% of this transformation. I've set up another example here in which I decided I would want to modify the shape of the stem. In this case, I've used surfaces as sources and targets. So if I hide that BREP, you can see that there's a small surface over here, and then I've manually basically created this new surface over there. I can control this by moving a point in space here. If I want this to look differently, I can just bring it back and forth. And again, if I apply the BREP morphing to this, you can see that the BREP transforms from the old shape, with the design variable being 0, all the way to the newly created shape of the stem. I could also make this more than 1 and then have it go beyond this limit here. And then finally, I have one more BREP morph that I've introduced here, which I wanted to use to change the shape of this knuckle line here. Maybe if I hide these sections, should be able to see that better. So there is this knuckle contour curve, which I've extracted here. And I've just written myself a little feature that takes this curve and allows me to change it in shape. We're looking from the top right now. I'm hiding the hull for a second. Through the use of those 2 design variables, so I can bring the endpoint basically out like this. Or if we look from the side at the ship, from over here, I can also move the endpoint up and down through this design variable. And you can already see that the hull follows along. Maybe I could increase the upper bound a little bit here so that you can see better. Just takes a second or two, and then the knuckle line is adjusted to this newly generated contour. And again, if I wanted to, I could put this factor in between, which defines if I want to match the new contour by 100% or just a little less. That's up to the user. So far, what I've shown, I guess, can be used in any type of application, although I've shown this here in the context, of course, of the offshore supply vessel. What's unique, I guess, to the naval architects amongst our customers is that they are always interested in hydrostatics when they do such kind of modeling. So you would at least want to always know what happens to your hydrostatics while you're doing all those modifications. And as you can see here, I've set up a little feature that allows me to plot certain hydrostatic measures that I've taken from the hull while I do all those modifications. So we can compare maybe what's the mid-frame area of our initial design, or what's the prismatic coefficient. It went down from 0.81 to 0.774 in this case here. Displacement is completely different, longitudinal center of buoyancy as well. And if these measures change, it might be the case that the designs we come up with are actually not that interesting because we have certain constraints on the prismatic coefficient or on the longitudinal center of buoyancy. We need those values to be fixed at the measures we started off with. To show this, maybe if I reset everything here and then change the shape of the midframe a lot by introducing a dead rise and flare angle. That gives us a completely different midframe shape. And you can see here, as soon as I update those measures, we also get a slightly different prismatic coefficient, and also the longitudinal center of buoyancy moves by 20 centimeters in this case. And what I can do, and I think this is to be considered the holy grail of partial parametrics for naval architects, is using a shift function to bring these characteristics back to where I want them. We call this a generalized Leckenby. And this transformation allows us to actually set those measures to exactly where I want them to be. So what I've done here, in this case, I've set up a Leckenby that is set up such that it would bring back the hydrostatics to what they were initially. So if we compare those measures here, you can see we have the exact same coefficient, the same prismatic coefficient as we started off with. And we also have the same longitudinal center of buoyancy. We're off by 1 centimeter here, but I think that's okay. While we have a completely different displacement, obviously because we have the same prismatic coefficient at different midframe areas, we have a different vertical center of buoyancy, we have different vetted areas. So those two design candidates will behave completely different while they both inherently fulfill hydrostatic constraints. That makes those two very interesting and worth considering. And what that means in essence is that we can now move on to an automated optimization procedure where we generate hundreds, if not thousands of designs, and all of those are feasible. All of those would inherently fulfill those hydrostatic constraints, no matter what they look like. And with that, I would like to hand back the presentation to Paolo to show us a bit more about the application case.
Thank you, Heinrich. I must say I'm very excited to start using CAESES 5 and these new functionalities with the BREP morphing. So this, after we have done the transformations, we check the hydrostatics, we advance towards weight estimations. We are back in the holiship spiral now. For this vessel, we had a required cargo deck area of 1,300 meters squared and 6,000 for accommodation. So we set up parameters that it will create as many levels as we need of accommodation until we fulfill 1,300 and 6,000, independent of vessel length and and width and the beam. From that, we apply constants of weight calculation, coefficients that from existing vessels and previous projects in order to estimate vertical center of gravity, how much dead weight we have, and finally check against hydrostatics and how much initial stability we have. And that is the first constraint we create for this project. If the vessel doesn't achieve at least 1.75 initial GM, the other calculations, it is considered unfeasible, and other calculations are not executed. Next step is writing arm curve stability check with NAPA and a crane drop load feature written in CAESES, where we check how much the vessel would heal in case we have a load hanging on the crane X meters outside of the deck. This is also second constraint. It's also considered the vessel feasible or not, and if it's a fail in IMO criteria, for example, we don't execute further calculations. We then start a motion estimations. That was done with ShipX by SynTef. We transformed that whole those sections, the whole surface to sections for ShipX. When in CAESES, we parameterize row reduction tank and bilge kills. We get response amplitude operators and a limiting operation for our crane. So we put limits for acceleration on the tip of the crane, and if and ShipX then calculates if above 3 meters HS is okay or not. From that operability limits, we get an operability in percentage for a given scatter diagram for a given position where the vessel is supposed to operate. This is a KPI that we use to choose the best designs during optimization. We proceed then to station keeping. That is another ShipX plugin. It uses various output files. We calculate projected areas from the accommodation we calculated previously in steel weight, and we give positions of the thrusters, the types of the thrusters, what are their limiting angles they should not operate, and so on. And ShipX returns us what is the thrust required to keep DP for that wave, for that environmental condition in each propulsor, in each heading. We go then towards resistance. We have a ship flow panel code estimation. This is the calculation from in the cycle that usually takes the most of the time, and for that we have we include surrogated models. So we pre-calculate resistance for our design space with, I believe in our case was over 500 design variants, and we get for each beam and length, you get 500 points. You generate a surface, and for new points that you are inside that design space, you can just interpolate the optimized the delivered power required for sailing. This then goes through the combination of thrust required for sailing and thrust required for DP goes through a feature that we wrote, and it checks inside our propulsion catalog which one is the cheapest that can fulfill the task. So the smallest possible. We have, of course, the highest diameter, but the smallest unit to reduce CAPEX and OPEX in the operation. And this then, the chosen proposal goes to Cosmos, which is a fuel estimation external tool provided by DNVGL, and with a simplified operational profile of 40% sailing, 40% DP, and 20% harbor, it gives a fuel consumption for some engine combinations. In our case, we had 4 engine combinations for this vessel. So now we have from hull design to stability, intact stability, we have motions, resistance, and DP operation, and we get what would it be the yearly fuel consumption for this design variant, this hull that we just created. So now we go to the optimization part, and to make things fair, we said, okay, at least for 4,500 tons of deadweight capacity for all design variants, at least 1.75 initial metacentric height, DP capability of 3.5 meters HS at a 30 degrees heading angle, 2 meters per second current, which is slightly high, 13 knots forward sailing speed, and we used results. We compared these results to a baseline design of UT 7623 of 2018. So all the results from now are relative to that baseline design. To check that everything is working as it should, all the connections, all the calculations, I started with a SOBO quasi-random that just fills the design space with 250 designs, and it goes through all the calculations, and we found out that everything was robust and we could continue to the optimization. In this phase, it was very difficult to identify trends because as they are randomly generated designs, you see this web of results that you cannot really pick why something is leading to this much fuel consumption or not. But still, we could see that clusters of fuel consumption were generated here, and that is then we identified that this is because of the thruster sizes. So as when you jump one thruster size, unit size, you jump in fuel consumption. So these explain these jumps here. In order to organize some of the design optimization routine, we then permuted the design space, increasing length and beam slowly. Draft was automatically calculated to give our required deadweight. So shorter and narrower designs have higher draft in order to give 4,500 deadweight capacity. As you can see on the right side, the intact stability, the GM, was the decisive factor of unfeasible and feasible designs. So for each length, we can then calculate, we apply a Brent algorithm in CAESES that calculates for this length, what's the minimum beam vessel width that would give us acceptable GM. And that creates a Pareto line basically of feasible design variants, which would be narrowest, which means lower capex, also lower resistance, and DP varies from design to design. But then we can see where we should be focusing. So these colored lines here, we can follow them back to a region of length and beam that we are reaching lowest fuel consumption as now. And finally, we settle in a design that is somewhere in this Pareto line, close to it. And just by choice, we end up with a shorter vessel, much shorter than the starting one, but wider. That means that we have a different arrangement of accommodation and cargo space that gives a lower fuel consumption thrust required for DP operations. As this vessel doesn't have very high speed, they don't need to reach 16, 17 knots usually. the DP thrust fuel consumption was more important than sailing. And it's more interesting for this project to have a shorter vessel and slightly wider. Achievable reduction, 5% in capex, mostly due to the lower, the shorter vessel, and a 6.3% in OPEX. This design then follows through phase 2, which was power system design and optimization, partially done with MPSat, a tool developed and used by Kongsberg. It runs to a database of engines, combine all of them, alternates current, direct currents with or without batteries. You can also size the batteries, and you get fuel consumption emission reports. So this design from MPSat, I'm not going to detail because it's more interesting for us at phase 1 in this webinar, but we can always talk about it later. Cosmos then do detailed battery size and a strategy study for the power management system, and then Buddha by Sirena and Buddha Veritas did this reliability analysis to estimate ship availability and reliability throughout the years due to different engine combinations or different batteries as well. And in phase 3, we take the design from phase 1 and 2, and we verify it in a dome simulator, where we test the loss of generators, the thrust failure, in case of a thrust failure, or the blackout of a whole switchboard. And we verify if this design is over dimension or under dimension, if it's able to keep position or not. And this is all in real time domain simulator. Yes, so that is mostly the work that we executed in Holiship. And additionally, we had a short spin-off of damage stability. Other work packages in Holiship were developing it, and we said we should also try to work with damage stability in CAESES. So the idea here is to create flexible arrangement. These vessels are very specialized, and tank arrangement creation is very complex. It's very irregular, but it ends up that the more tanks you have, the better you will reach your damage stability index required, but also the cost of the vessel increases. So how can we start with a design, a tank arrangement, initial tank arrangement, that is as clean as possible and get as high a attended index as possible? So we try to recreate the arrangement in CAESES and make it talk with NAPA, generating as many as we need, as many as we want to investigate. So we start creating the bulkheads, and these are aft collision bulkhead, fore collision bulkhead, engine room bulkhead, and so on. And I try to parameterize it as an example, how many additional aft cargo subdivisions we should have, how many wing tanks subdivisions along with the engine room tank, what is the position of the engine room, what is the length of the engine room. The same for the collision bulkheads and row reduction tanks, for example. And this is all somewhat flexible. As long as you know what you're looking for to optimize, we can always reparameterize these and investigate a different arrangement that you're interested in. We then need to generate the longitudinal bulkheads, and these can get very complicated. We keep it as similar as NAPA as possible to make it easier for other people that is used working with Napa can work with CAESES in the future. And we can also create these longitudinal bulkheads, make them snap to bulkheads or points or offsets from the hull, so we know that it satisfies at least, let's say, 1 meter from the outer hull. That is for construction purposes or for damage and clearance purposes. So that we can always find and generate, automate this creation. Then we need to do the same for the deck levels, and they are somewhat easier. You can see are just flat, but some of them also have steps and different arrangements. And this can also be, you can see on the feature on the side here, how I can make it always snap to a certain bulkhead position or a frame number, for example. And when we have the hull, the longitudinals, the bulkheads, and the decks, we can make an intersection of these surfaces and create a solid tank. And when you create the tanks for the whole vessel, you're able to generate an arrangement in APA and calculate damage stability. So here's part of the code that we create all the bulkheads, all the transversal bulkheads, the longitudinal ones, and all the room creations. So the features give strings that are recognized by NAPA, and when we run NAPA in the background, you can see how we get exactly the same vessel that we are seeing in CAESES and so on. We then run to the calculation script, and we get plots of damage stability from 1 zone, 2 zone, to 3 zone damages in deepest draft, partial draft, and light margin draft, and you get also tank arrangements and so on. So this is my final slide before the live demonstration, and you can see this is one of the optimizations we recently run. So these are plots of the tank arrangement in NAPA, and this is the tank arrangement being generated in CAESES, and how design variables generate different numbers of bulkheads, different position of longitudinal bulkheads, and also tank subdivision subsequently. So I would like to move it towards CAESES here. I've been starting to use CAESES 5 as well. Seen some a good amount of response and increase in speed. And here I'll do a very quick demonstration. So from engine room bulkhead aft until engine room bulkhead 4, I have 2 engine room wings. And in this case, I did a pre-run, and we attained a damage stability index, attained index of 0.764. But what happens when I reduce? Do I really need this extra engine room here, this wing subdivision? So I can easily go to my wing variable, reduce it to 1. CAESES will start updating the features. So the first thing is that it creates the bulkheads without the extra wing bulkhead, and then it generates all the tanks between with a loop. All the tanks between aft engine bulkhead to 4 engine bulkhead. It generates now only 1 wing tank, and now I can go to my NAPA connector and just call NAPA and run an stability check there. So now CAESES is exporting the whole geometry. It's starting NAPA in the background here. Will pop up. So NAPA checks for licenses at the moment. It then starts running our damage stability script. It first generates all the tanks, all the bulkheads, imports the geometry, generates the tanks, and starts creating damage cases and healing the vessel if in case of damage. And when the result is done, it starts plotting this, all the plots in the area, and exporting these files as images and even AutoCAD versions of the tank drawing. And now CAESES has updated, and now I have the results. So I can go to the results here with a damage stability engineer, and we can see that our index dropped by 2.02, just from 0.76 to 0.74. And maybe this is a margin that it's something we can work on and save a lot of tank construction there. I did a pre-run earlier, bearing also not only the amount of wing subdivisions, but also the engine room position and the engine room length. So, for example, here I can go through with my engineer to the results, and we can check also how many tanks that arrangement had. So we probably want a design with fewer amount of tanks and a higher attended index. So we can go to this design variant 0.75, and we see that this is a somewhat good because it has only one wing subdivision. Unfortunately, the engine room position is located further aft and not the shortest we could have. And this would give us slightly less cargo capacity. But that is some these judgments we need to make and know when to which one is acceptable or not. So we can also filter by, okay, I want to put an engine room that is further forward to give more cargo capacity and still have a lot of attended index. Only 2 wing divisions, quite long engine room though, and so on. I can always go on the detailed results of that design as well and talk with my engineer and see what should we optimize next. So that's all I had to present for today. Thank you very much for your attention, and we have a few minutes for questions, and please just give us your thoughts. Thank you.
Right. Thank you very much, Paolo, for this impressive, I think, case study presentation. A lot of very advanced things that have been done there, advanced features and cases, and many aspects that were taken into account. Thank you also, Heinrich, for your very concise presentation of the possibilities that are offered by partially parametric modeling in CAESES. Indeed, we have a few minutes left for some questions, and I have a few questions here. I'll just start off with something I can answer myself very quickly. One question was regarding if the model that was shown, I think maybe mostly in Heinrich's presentation, if that is available as a sample or tutorial in the software. That's not the case yet. In the software, we have a few other samples that you can find. And if you're looking for to, I don't know, find out specific things, then maybe get in contact with us and we can provide also some additional material going further than what you can find in the software package as you download it. Also, there was a question regarding the freeform deformation method that someone did not find it in the software as it came from the website. That should be available there. So the freeform deformation is basically a standard functionality as well as the morphing capabilities, other morphing capabilities that Heinrich showed, and they should all be available in CAESES 5 in the model workspace. In the CAD tab, you have a menu for morphing, and you should find this functionality there. So there is a question, I think this could be mainly related to Paulo's presentation. Could such a complex design task, could that have done using a, let's say, conventional approach at all? And if yes, would that have taken longer? And would you expect that the performance of the optimized design found now is considerably better than using a conventional design process? What do you think?
Yeah, thanks for the question. I would say traditionally you have a rather limited time to go through the design spiral, and that doesn't give you enough time to explore the whole design space traditionally. But when you start with a holistic setup of tools, that calculation time is reduced a lot, and you can investigate more designs. So I would say it's not that you cannot reach the optimal design traditionally, but you need more time. You would need you need a lot of expertise and more time together until you get an optimal result.
Yeah, makes sense.
Holiship approach, maybe you're able to reach it faster.
Yeah, this holiship approach that you have shown here, that was obviously developed in an R&D project, and this case study was also part of the R&D project. Is this something that you are already using for commercial projects, or do you plan to introduce this methodology also in your commercial projects?
Oh yes. So many of the projects they are not interested in all the KPIs, the parameters at once, but it's very often we are interested in mostly in, for example, motions on a specific vessel, and we just plug in the hull and run the motion calculation with this setup, or for resistance, combination with DP resistance, something. So yes, it's rising and rising the usage of this methodology.
Oh, great. Yeah, something for Heinrich. You talked about hydrostatic constraints that can be fixed during the optimization process. And there is a question here regarding, could they also be loosened or maybe set to a specific range to take into account design candidates that are a bit further off with respect to their hydrostatic characteristics?
Yeah, thanks also for the question. Definitely, yes. So one way could just be to make these variables actually design variables. So when I said that prismatic coefficient or longitudinal center of buoyancy would be fixed, I could just as well make them a design variable and change them throughout my study. But I could also just skip the Lackenby transformation in the very end and say I'm happy with whatever I get after all of my transformations. And that would then leave me with a number of designs that have completely different hydrostatic characteristics. And then I could just use constraints through or during my optimization procedure and say I want to limit my feasible design space to longitudinal center of buoyancy between, I don't know, 49 and 49.5% of the length of the ship or something like that. So yeah, definitely okay. They can be loosened.
Thank you. I have a few small questions that I think I can also directly answer. Parametric deformation, is this possible to apply on a model generated in NAPA after importing it in CAESES? Yes, that's possible. You can export geometries in NAPA in IGES format and import them in CAESES as a surface model. We have also some cleanup functionality, because sometimes the Napa models have a lot of surface patches and they need a little bit of repair to have a clean geometry. And then we can apply all these deformation methods that Heinrich showed to these imported models. Does CAESES have a hydrodynamic calculation module? This is not the case. We connect to external CFD solvers for the hydrodynamic calculation. And another question was propulsion power calculation by holiship method. Yes, this is something that can be implemented in CAESES. We have this feature scripting environment that was mentioned a few times already, and I'm not sure if we have done it already for the holiship method, but this is something, yes, you could easily include directly in within CAESES. Propeller design in CAESES is also possible. We have dedicated functionality for propeller modeling, and there was a question about papers. We can provide some material on that further later on. All of these new design functions that you have included in CAESES 5, do they replace the feature definition editor with function scripting? No, the feature definition editor in CAESES 5 is still available as it was before, and most of these things that have been shown here are also based on feature programming. Yeah, I got a note from one of my colleagues here. The holiship method was indeed included or implemented in CAESES. This was work that was done by the University of Strathclyde. So as I imagined, this is something that has been done already. Maybe one question for Paolo, possibly final question. The feature for the compartmentation looked very nice. This was, of course, tailored to this vessel. How quickly could it be used for a different vessel, and would it require a lot of adaptation? What do you think?
Yeah, thanks for the question. We have used already for other vessels, and as it's still under development, it took more than I wished. But still, it depends a lot on what you're interested in to optimize, right? So if you want to investigate the amount of wing subdivisions or the length of specific, so then you don't need to parameterize everything, the whole vessel. You would put design parameters only in that area that you're interested, and that makes things a little bit faster. So the tanks features, the bulkheads and tank generation, they are generic. So you can just pull the feature to a new project and start generating the tanks. You don't need to reprogram, or it's not one tailor-made for this project only. So I made it as generic as possible so that we can use. And if I do the next project by myself, it doesn't take more than 6 hours to generate a full arrangement. If I'm working close to the designer of the vessel and the stability engineer, that he knows where he wants things and so on, it doesn't take long until we start optimizing it. Thank you.
Okay, great. I have one final question here. Are there any major drawbacks in this new approach that you can think of?
Is it for the whole?
For you maybe, or for yeah, maybe just your opinion, Paolo. I think that.
Yeah. Let's say I'm too new to the industry to judge how effective the old process was. So I'm part of this new generation coming with the holistic design, and I'm not able to say that it's more efficient or better in any way. I'm using it, and I then show it to my my supervisors and my bosses and the design engineer. How fast can we do, and what results can we achieve? And then they have to do their judgment.
So, yeah, fair enough. All right, I think that's all the time we have for today. We're slightly over time, so let's come to an end. Just some final information. CAESES 5 was mentioned a few times by Heinrich, but also by Paolo. There's going to be a webinar coming up next week on Wednesday, January 27 at 2 p.m. Central European Time. If you want to learn more about a new functionality in CAESES 5, register for that webinar. And then this was the second application case webinar based on the application cases from the holiship project. And there's going to be a next application case webinar together with Naval Group coming up. The final date is not set, so watch out for the announcement in the event section on our website. You can also find the CAESES 5 webinar in that event section. And of course, if you have any questions or you need to get in contact with us for some reason, feel free to send us an email, or in our case at least, you can also use the contact form on our website. So, as I said, this is all we have for today. Thank you very much for attending. Stay safe, stay healthy, and I hope to see you or hear you soon. Goodbye.
Thank you very much from my side as well. Goodbye, everyone.
Thank you. Goodbye.
Bye-bye.